In this video, we're going to talk about rational functions. So a rational function is the division of two polynomial functions, and we're assuming this rational function is in lowest terms. Okay? The domain of this rational function is a set of real numbers such that the denominator does not equal 0. So I've written two examples of rational functions. So now what I would like to do is to write the domain of each of these rational functions in interval notation. Okay? So let's start with x minus 2 divided by x squared minus 7x plus 10. So again, domain restrictions are going to be when the denominator is equal to 0. So we want to eliminate those values. Okay? This is factorable. Factors of 10 that add up to be negative 7 are negative 5 and negative 2. Okay? Set each factor equal to 0. And we have x equal to 2 and x equal to 5. Put this on a number line. Okay. So again, these are the only two numbers. So that means all numbers smaller than 2 is okay. All numbers between 2 and 5 are okay. And all numbers bigger than 5. So there should be 3 intervals for my domain. Negative infinity to 2, or 2 to 5, or 5 to infinity. Okay, one other one I want to take a look at then. So again, I'm going to set the denominator equal to 0. Okay, so I can subtract the 9 and take the square root. Square root of negative 9 is 3i. So here would be plus or minus 3i. So again, those are not real numbers. So we're not excluding anything here. So the domain is all real numbers. Another way you can look at that is we know that you take any number and square it, it's either going to be 0 or it's going to be positive. And when I add that to 9, that is never, the denominator will never be 0. So we know the domain in this case is all real numbers. Just because I have variables in the denominator does not necessarily mean I'm going to have domain restrictions. Okay, so now I want to take a look at the function 1 divided by x plus 3. I want to start off with determining what the domain and the range of this function is in interval notation. So I have done this graph on Desmos. Okay? Now, with the domain here, I can tell somewhat quickly that x cannot equal 0, but it looks like every other domain value is included for this. So the domain is going to be negative infinity to 0 or 0 to infinity. All right, now let's talk about the range then. So for the range, or the y or f of x values, they look like all taken care of, except it looks like it's very, very, very close to 3, but it's never going to be 3. Okay, let's go back and take a look. When I take any number and add it to 3, you are never going to get 3 because this fraction 1 divided by x is never going to be 0. So I know we have a range restriction and it can't be 3. So negative infinity to 3 or 3 to infinity. Okay, now let's take a look then. As x approaches 0, that plus means approaching 0 from the right-hand side. So let's take a look then back at Desmos. If I'm approaching 0 from the right-hand side, see where the arrow's going? That's going up to what? Positive infinity. So let's write that in. Now, this one is telling me as x approaches 0 from the left-hand side. So let's go back to Desmos. Okay. From the left-hand side, see where this graph is going? That is approaching negative infinity. Okay. Another way I can say that are limits, okay, in case you take pre-calc or calculus. Okay, now we want to know about the end behavior. As x approaches positive infinity, where are the range values going? And as x is approaching negative infinity, what is f of x approaching for this? Well, let's go back to the Desmos then. Okay. As x approaches negative infinity, it looks like I'm approaching what? 1, 2, 3. And as x is getting bigger and bigger and bigger, it looks like it's approaching what? 1, 2, and 3. So it looks like they're approaching the same particular value. So it's nice to see that not all n behaviors are going to be either positive or negative infinity. They could actually be a number also. Okay? So to summarize, are there any f of x values such that x is going to be 0? Answer is no, because that is 0 is not part of the domain. Are there any values of x such that f of x is going to be 3? Answer to that question is no, because the range values does not include 3. Okay. Now, why am I showing you this particular graph? Well, there are two types of asymptotes that this rational function has. And asymptotes are lines that the graph of a function approaches but may or may not cross. Okay? The first one I want to talk about is what is called a vertical asymptote. So, if f of x either increases or decreases without bound as x approaches a from either side to the left or to the right, then x equal to a is what is called a vertical asymptote. Vertical asymptote looks very similar to a vertical line. And I write the equation of a vertical line, x equal to a number. So let me go back to Desmos very quickly. You can tell the vertical asymptote looks like it's x equal to 0. Okay, that would be the vertical asymptote for this. Okay. Okay, so fact, a graph will never cross a vertical asymptote. Okay, again, we will assume the rational function is simplified. The graph of f has a vertical asymptote at any real 0 where the denominator is equal to 0. Okay, so let's determine and write the equation of the vertical asymptote or asymptotes. So again, where do I go? Denominator equal to 0, as I'm going to move this down slightly. So set the denominator equal to 0. Okay. All right, so this does factor. This is 2x minus 1 and x plus 3. Set each equal to 0. Okay. So I'm going to write VA for vertical asymptotes is x equal to 1/2 and x equal to -3. Now I want to take a look at the Desmos for this then. So again, you can tell two vertical asymptotes. Here's one at x equal to 1/2, and then the other one, 2, at x equal to -3. So in this particular case, the graph shows we have two vertical asymptotes. Okay, now let's take a look at one other example then. Okay. So now again, what would I do? I would like to set the denominator equal to 0. Okay, and again, this is factorable. And we know x is equal to 4 and x equal to 3. So if I graph this on Desmos, I would expect to have, again, to have two vertical asymptotes for this. Well, let's take a look at the Desmos then. Okay. So I'm going to get rid of this and put this. Now, what do you notice? I don't see two vertical asymptotes here. In fact, the only vertical asymptote I see is at x equal to 3. I do not see one at x equal to 4. All right, so let's go back to the original problem then, and let's figure out why. Well, again, we know this is not the case. Now, why? Well, let's factor the top two. Now, this is not simplified, meaning I can divide out a factor of x minus 4, and now I have just x minus 3 in the denominator. So my vertical asymptote here is x equal to 3. Now, what does happen at x equal to 4? Okay. Well, let's see if we can show that on Desmos. Okay. So at 4, it is a hole, because look, it's undefined in the graph here. So this is what is called a hole in the graph. Okay. So if I scroll down, so x equal to 4 is not in the domain still. Okay, but it's not a vertical asymptote. It is a hole in the graph. Okay. Okay, so now let's talk about another type of asymptote, which is called horizontal asymptote. If f of x approaches b as x increases or decreases without bound, then the line y equal to b is a horizontal asymptote, just like the equation of a horizontal line, y equal to a number. Horizontal asymptotes imply that a function approaches a constant value as x gets larger in either the positive or negative direction. Okay, so let's take a look at a couple of these then. Right? So as x approaches positive infinity, where does f of x equal to 1 divided by x go? Well, if x is very, very large, I'm taking 1 divided by a very, very large number, and that's going to approach 0. So f of x would approach 0. Okay? Now, if I have something like x divided by x squared, similarly to what I just finished a minute ago, I can divide out an x on the top and the bottom, and now I'm back to 1 divided by x. So in this particular case, again, as x is going to infinity, or approaching infinity, f of x is approaching 0. So notice, the degree of the numerator for both of these is smaller than the degree of the denominator. Now, let's take a look at the third example. As x approaches infinity, where does f of x equal to 3x squared divided by 2x squared go? Well, 3x squared divided by 2x squared is 3 halves. So this one's nice. F of x is going to approach 3 halves. Okay. Now, as x approaches positive infinity, where does f of x equal to x squared go? Well, you take a very large number and square it, it's going to get a whole heck of a lot bigger. So f of x is going to approach infinity. Okay. Well, how about f of x is equal to x to the 4th divided by x? Well, I can divide out an x from the top and the bottom, so x to the 4th divided by x is x cubed. And when I take a very large number and cube it, I'm going to get even a larger number than that. So f of x is going to approach infinity. So if the degree of the numerator is bigger than the degree of the denominator, it doesn't look like it's going to approach a number. And the third example, this one here, if the degree of the numerator is exactly the same as the degree of the denominator, then it looks like what? The leading coefficient for both the numerator divided by the denominator. Okay? All right. Now, one way I can show these horizontal asymptotes is I can divide every single term by the largest exponential power and use the fact of what we tried to do up here a minute ago to try to guess where this horizontal asymptote is going to be. Okay? All right, so let's take a look at one then. So when I take a look at this rational function, I notice x cubed is the largest exponential power. So I'm going to divide every single term by x cubed. Well, 3x squared divided by x cubed is 3 over x. That does not simplify. On the bottom, that's 3 minus 1 over x plus 4 over 4 divided by x cubed. So 3 divided by x, that gets very close to 0. Not exactly 0, but approaches it. Plus about a number very close to 0 divided by 3 minus 0 and plus 0. So that's about 0 over 3, okay, which equals 0. Okay? So I would expect the horizontal asymptote for this rational function to be y equal to 0. Now, we can check this using Desmos. Okay? So I'll get rid of this and put this in. And you can tell as x is getting very small or very, very big, the range values are both approaching 0 for this. So that is where our horizontal asymptote is going to be located at. Okay. So let's do two other examples with this. Again, I would like to do the same idea, and then we can talk about a general way to do this. So again, notice the highest exponential power for g of x is 5. So I'm going to divide everything by x to the fifth. Okay, so it simplifies 10 divided by x to the fourth minus 3. And that's what? Negative 1 divided by x cubed minus 3 divided by x plus 1 over x squared. So that's what, about 0 minus 3 divided by 0, which is negative, minus 0 plus about 0. So you're talking about negative 3 divided by a number that is very, very, very close to 0. Well, if you put in negative 3 divided by a very, very tiny number, in fact, why don't I do one right now? If I put this into my calculator, in fact, we'll do this. Okay. And if I put that into my calculator, I end up getting this. And the closer I get to 0, the larger that number is going to be. So that is not approaching anything. So in this particular case, we have no horizontal asymptote. Okay. Now, what I would like to do is to check the Desmos for this. Okay. We'll go back. So we will unhighlight this and put this in. Again, as x is getting very, very, very big, notice it's not approaching a number. It's going to positive infinity. As x is getting very, 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 very small, f of x is not approaching anything. It looks like it's going to negative infinity. So there is no horizontal asymptote. And again, the degree of the top is 5. The degree of the bottom is 4. Okay, we don't have a horizontal asymptote here. Okay, one other example I want to take a look at then. So again, notice here, the highest exponential power is 5. So I'm going to divide every single term by x to the fifth. Okay, so this simplifies negative 1 over x plus 3 minus 1 divided by x cubed. And on the bottom, 4 minus, looks like 6 divided by x minus 8 divided by x to the fifth. So we're looking at about what? About 0 plus 3 minus about 0 divided by 4 minus about 0 minus about another 0. So we're going to be awfully, awfully close to 3/4. So I would expect the horizontal asymptote for this to be y equal to 3/4. Okay. Now, let's check the Desmos for this. Okay. So I highlight this again. As x is approaching negative infinity, it looks awfully, awfully, awfully close to 3/4. And as x is getting bigger and bigger and bigger, it looks like f of x is approaching 3/4. Okay. So what do you notice about the degree of the numerator and the degree of the denominator? They are exactly the same. The degree of that trinomial on top is 5, even though it's not in descending order. And the degree of the trinomial on the bottom is also 5. Okay, so now let's come up with some general rules for this. So when locating horizontal asymptotes, when the degree of the numerator is smaller than the degree of the denominator, then where am I going to locate my horizontal asymptote? Well, it'll either be the x-axis or as an equation, y is equal to 0. Very, very similar to the very first example we looked at. Now, if the degree of the numerator is the same as the degree of the denominator, then what am I going to do? That is going to end up being y equal to, well, that's going to be a of n, the leading coefficient in the numerator, divided by the leading coefficient in the denominator. That was the example that we just finished doing here. Again, leading coefficient in the numerator is 3. The leading coefficient in the denominator is 4, so we end up having 3 4s. If the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. So again, you can either do the algebra like I've done earlier in this video, or if you understand these 3 general rules for this, you can identify if and when we have a horizontal asymptote for any rational function.